What? Too much?
Too much.
Okay. Welcome to Too Much Chem. My name's Johanna Brown. I teach chemistry most days of my life, so now I'm just doing it on video. Okay, today is all about bond polarity, which is going to lead into molecular polarity and intermolecular forces and vapor pressure. We're going to do tons with this. So this is really foundational stuff. But even before you feel good about bond polarity, make sure that you have a firm understanding of electronegativity. I'll redefine it today, but that's something you should feel pretty comfortable with before you move on. So, electronegativity is a measure of how good an atom is at attracting electrons to itself. So, it's kind of like hot or not for atoms. So, how attractive they are, right? And electronegativity, it seems like a weird word and like maybe it doesn't matter, but as we move into the stuff we're talking about in the next few episodes, you really have to feel good about it. So electronegativity is how good an atom is at attracting other electrons. Okay, so why does this matter? Well, it comes into play in bonding. When atoms get close to each other, their electrons might be overlapping in orbitals or electrons might be transferred. So we need to understand when that's going to happen, all right? So we're going to be talking about different atoms today and looking at their differences in electronegativities, whether they have small differences or big differences. So I'm going to ask you a couple questions. I want you to think through it with me. If we put two atoms together that have the same exact electronegativity, what do you think is going to happen to the electrons that are between them? Well, this might happen with fluorine. So fluorine atoms all have an electronegativity of 4. They're really strong. But if you have two things that are very strong and they're pulling equally, it's kind of like tug of war. Are we going to have any movement on those electrons? Well, no. So when you have 0 difference in electronegativity or a very low difference in electronegativity, we'll actually see the electrons being shared evenly. So you can see I've just drawn electrons. It's kind of a probability model. So we see that they are dispersed equally between the two fluorine atoms. We call this a non-polar covalent bond. Covalent because the electrons are being shared, and non-polar because there's no pole, there's no charge occurring here. Okay, that's the first one. Let's think about what happens when we put two atoms together that have a huge difference in electronegativity. We're talking a super metally metal and then a supery non-metal. Let's see, something like sodium and chlorine. Those were very scientific terms, write them down. Okay, when we put things like this together, when they have a very big difference in electronegativity, chlorine's is high, sodium's is low. Chlorine is so much stronger than the sodium in terms of attracting electrons that they don't even share. Chlorine's over that. It takes the electron from sodium and becomes this chloride ion, right? Leaving the sodium ion here. So hopefully you've already learned in other classes that ionic bonds are taken, not shared in terms of their electrons. So that's why that's happening. It's because chlorine is so much better at attracting electrons to itself. So we call those ionic bonds because the ions are then what bond. Okay. So of course in chemistry there are exceptions. We tell you 2 rules and then there's always something in the middle. True? In the middle here is when the difference in electronegativity isn't so huge that electrons are taken, but they aren't exactly the same, so they're not shared evenly. They're still shared, so we call it a covalent bond, but what we see is the electrons end up spending time with the atom that is more electronegative. So in our example here, we have hydrogen in chlorine, and you'll see the electrons are distributed more around the chlorine. Remember, this isn't the number of electrons, this is just a probability model of where the electrons are. So they're hanging out with chlorine a little bit more. So we see this partial negative charge on this side of the bond, partial positive charge on that side. And we know that positive and negative charges really feed into our understanding of what happens in molecules and atoms, right? Okay, we call this a polar covalent bond. Has a slight charge, uneven sharing. Wonderful. So what does this mean for us? What is going to be asked of you in your chemistry class? Well, oftentimes you'll be given the 2 atoms that are bonding and you'll need to tell us what type of bond is occurring. What's nice about this is we have some very firm rules, and as long as you can follow those, you're going to be good to go. Let's look at how this plays out. So you'll see I've drawn a spectrum up here. So we go from non-polar covalent with a very low difference in electronegativity all the way up to the huge differences in electronegativity where we see ionic, okay? And so as humans, we love putting things in boxes. So what we've done is we have assigned values where the transition occurs between non-polar covalent and polar covalent, and then between polar covalent and ionic. So I'm going to tell you what those are. So if you have a difference of electronegativity that is below 0.5, okay, so these 0.4s and below are all non-polar covalent, okay, that's just what we consider them. Now, when we look at polar covalent, that's from 0.5 up through 1.6. All of those are polar covalent. They are shared, just not evenly. And then anything above a 2 is considered ionic. You might have noticed we have a little gray area in here, right? We have some overlap. So the way you're going to determine that when you're looking at things between 1.6 and 2.0, if it's a metal and a non-metal, we call that ionic, okay? If it's a non-metal and a non-metal, we'll call that polar covalent. Let's do a little practice with this just to make sure we are all on the same page. I've got a couple of different elements listed out here. Here we have some elements laid out similar to their arrangement on the periodic table. Of course, there are a lot of things missing. Hopefully you're noticing the trends in electronegativity that you should expect at this point. So we're going to just bond some of these elements together and classify what type of bond we would see between these. So let's start with hydrogen and oxygen. Hydrogen's electronegativity value is 2.1, oxygen's is 3.5. So the difference between those is 1.4. 1.4 puts us firmly in the polar covalent section, so good to go on that one. Next one, we're going to combine lithium and chlorine. So instantly, I'm hoping you're thinking, I have a metal, I have a halogen, this should definitely be ionic. Let's make sure that the numbers support our understanding. Lithium's is 1.0, chlorine's electronegativity value is 3 for a difference of 2, which is definitely an ionic bond. Good. Next, let's do carbon and hydrogen. So carbon and hydrogen, these make up a lot of lipids that you may have talked about in biology class. So we'll talk about why they're so important. We've got an electronegativity value of 2.5 for carbon, 2.1 for hydrogen. Their difference is only 0.4, making them non-polar. And that's why they're those hydrophobic tails you see in cell membranes. They're non-polar. They make fats, waxes, oils, etc. Okay, cool. Final test to make sure we totally understand what's going on. We're going to put a hydrogen and a fluorine, the most electronegative element of them all. We're going to put these together and see what happens. We've got a 2.1 and a 4.0 for a difference of 1.9. Now, remember, that's in kind of our gray area. So we have to think, do we have a metal and a non-metal or two non-metals? Well, hydrogen and fluorine, even though we found a little research to support that sometimes hydrogen can be a metal, we're still going to call it a non-metal. So that means that this is also polar covalent. Okay? Hopefully that helps clear up some stuff about bond polarity. Next week we'll look at how this feeds into the polarity of an entire molecule, and I can't wait to see you then. Thanks for watching.